In our last video, we started looking at the limits at infinity of a rational function, and we looked at this kind of simple example of 3x plus 1 over x minus 2. And what we decided was that the constant terms were not significant as the x values were getting bigger and bigger. And so we were able to just ignore them, and that let us cancel out the x's and come up with an answer really quickly. Let's take a look at some other functions though, and we'll see that the situation isn't always the same. All right, in this case, I will look at the limit as x approaches infinity of, let's say, x squared plus 4x minus 3 over 10x plus 38. All right, so I want to approach this the same basic way that I approached the last problem and see if that works out for me. That's a good problem solving strategy. If you've got a problem you haven't quite seen before, you can try solving it using old techniques and it'll either work for you or you'll get stuck at some point in the way, but at least you'll have gotten a start. All right, so let's look at this and figure out which terms here, if there are any, that are insignificant. What do you think? Well, in the numerator, I think this -3 is insignificant. That's pretty boring. All right. How about this 4x? Is this term insignificant? Well, this term is growing as x is growing, but it's really not growing as quickly as this x squared term is. So when x is 10, this term is 100 and this term is 40. They're pretty close to each other. But when x is 1,000, this term is 1,000,000 and this term is 4,000. 1,000,000 versus 4,000. So this term is really falling behind in significance. And let's imagine a million. A million squared is 1,000,000,000,000, and this is only 4,000,000. So a trillion, think of having $1,000,000,000,000 versus having $4,000,000. This guy with $4,000,000 probably thought he was pretty rich, but there's nobody in the world that's so rich that they have $1,000,000,000,000. All right. So once again, we can see that this term is insignificant. And in general, we're going to see that when we look at polynomials approaching infinity, only the leading term, the term with the highest exponent, is going to be significant. So we can ignore all of the other terms. And in the denominator, same trick as before. We'll just eliminate that constant term because 10x is much more important. I'm not thinking about the x squared down here because the x squared isn't affecting the value of the denominator. It's only the 38 and the 10x. But out of these, the 10x is the only one that's going to remain significant as x is growing larger and larger and larger. So once again, we're going to say that that's equal to the limit as x approaches infinity of x squared over 10x. All right. The next step we took in the problem we did before was we saw if we could simplify this fraction. And the answer is yes. We've got x terms in both the numerator and the denominator. So I can cancel out one of the x terms in the denominator. What does that leave me in the numerator? Well, I've got x to the second power, so dividing x by that is just going to reduce me down to x. So now I've got the limit as x approaches infinity of x over 10. What's that equal to? Well, now we've got one of the rules that we were using in our earlier videos, that we've got a case where x is approaching infinity in the numerator, but the denominator is staying constant. And so we remember that that is equal to infinity. All right, and so when we had this complicated polynomial, let's take another example here. So we've got the limit as x approaches infinity of, let me be really wild here, x to the fourth plus 3x cubed minus 10x squared plus 147 over x squared minus 150x plus 71. All right, so that's the limit as x approaches infinity of all of this mess. That looked like a very complicated problem earlier, but see if you can solve that and simplify it the same way we did in the earlier example and see if you can find an answer for that. Once again, the only terms we need to think about when we're looking at the numerator and the denominator are the terms with the highest power, which we call the leading terms. So in this case, that's not important, that's not important, that's not important. In the denominator, only the x squared term is important. So as x is large, of course, when x is not a large number, if x was 4 or something like that, and you were calculating this and trying to come up with an estimate, these numbers would have a really big impact on that fraction. It's only when x is a large number that we can ignore those when we're estimating what the value is going to be. So that's going to be the limit as x approaches infinity of x to the 4th power over x squared. And we can simplify that by dividing both the numerator and the denominator by x squared. That leaves us x squared in the numerator and nothing in the denominator. And that's obviously infinity. As x gets larger and larger, x squared is definitely getting larger and larger too. So that approaches infinity. So what we see when we're doing this is that whenever we've got rational functions, if the numerator has got a higher power in its leading coefficients than the denominator, the limit is always going to be infinity. All right, in the next problem, in the next video, what we're going to do is we're going to flip this around. We're going to see what happens when the denominator has a higher power than the numerator.